The purpose of this little video here is to go over the steps that you need to complete in order to develop a valid Lewis structure. So the first thing that you want to do is you want to draw a skeletal structure of whatever your compound is. The second thing you want to do is count up all the valence electrons from each element within that compound to get a total number of valence electrons. The third thing you want to do is use those valence electrons to make bonds. And then after that, you distribute the remaining valence electrons around your elements as lone pairs until you have used all your valence electrons up. Now, not to be overlooked, you must make sure that the valence electrons counted up in step 2 match the number of valence electrons used in the structure you actually created in step 3. This is a step that students love to overlook, but I promise you it is quite important, because if you don't do it, you run the extremely dangerous possibility that you will not have a good Lewis structure, and certainly nobody wants that. So make sure you complete step 4. Step 5, make sure the octet rule is obeyed. Sometimes you'll be dealing with an exception, but for now, let's just say we're going to obey the octet rule. I'm going to explain this a little bit more, but this means that you have a total of 8 electrons distributed around your atoms. So if for any reason you don't have an octet and you have used the correct number of valence electrons in your structure, you might find that you have to move lone pairs to make double or possibly triple bonds so that the octet rule is obeyed. But let's do a simple example. Let's not make our lives too complicated for the moment. Let's just go with something like ammonia, which has the formula NH3. And we want, as in step 1, we want our skeletal structure. So we're going to do it. Note, most textbooks will tell you that you should put the least electronegative element at the center. In this case, I would say that's true generally as a good rule. Hydrogens, however, always go around the outside of your molecule. Pretty inevitable that the hydrogens are going to be on the outside. Okay, so now we have our skeletal structure. We need to count up the number of valence electrons, 5 for nitrogen plus 3 total for our 3 hydrogens equals 8 valence electrons. So as noted, we need to use bonding our valence electrons as bonding electrons first. So we're going to connect our nitrogen, our central atom, to all our hydrogens. How many electrons did we use? Well, we used 6, because each bonding pair is just that, a pair, it's 2 electrons. Notice, however, by making 3 bonds, we've only used up 6 electrons, so we have 2 more to go, because we need to use a total of 8, right? So now, the only place that this bonding pair can really go is around our nitrogen. So we're going to put it right there. Now notice, if we count up on all the electrons we've used in this structure, we have 2, 4, 6, 8. Isn't that glorious? 2, 4, 6, 8. Who do we appreciate? A good Lewis structure. Okay, so another thought. Have we obeyed the octet rule here? Well, let me rewrite this so we can see this a little more clearly. We certainly have obeyed the octet rule. We have 8 electrons in total surrounding our nitrogen. So these are the basic steps. Now, the truth about Lewis structures is, while it is imperative to follow the steps, practice is going to make perfect. There are exceptions, and you're going to have to develop a feel for this somehow, because it's just hard to do it, just obeying the rules. You're going to start to see what makes sense. You're going to develop almost kind of a level of intuition for what a good Lewis structure is. I do, however, have some tricks of the trade. which I think are actually quite helpful, and I hope you find them helpful too. We need to start this discussion from considering the typical number of bonds and lone pairs found in Lewis structures for compounds involving carbon, nitrogen, and oxygen. A lot of your Lewis structures that you're going to be asked to draw involve these elements, so they're good to focus on. And if you go on to organic chemistry, you're going to be seeing a lot of these as well. So in order to explain this idea of a typical number of bonds and a typical number of lone pairs, I want you to think about how we distribute electrons around each of these atoms, each of these elements, and that will help you make sense of the fact that carbon tends to make 4 bonds and have no lone pairs. Nitrogen, on the other hand, tends to make 3 bonds and have 1 lone pair. Oxygen, finally, tends to make 2 bonds and have 2 lone pairs. If you look at these electron dot structures right here, that makes a whole lot of sense, right? Because let's say we're adding a hydrogen with its 1 electron to carbon. Well, it's going to want to come in there and form a shared pair, right? So by virtue of having these single dots, carbon has 4 single electrons to share to make those 4 covalent bonds. If we move on to nitrogen here, nitrogen has these 3 single electrons that are available to make 3 covalent bonds by sharing a single electron with another element. And it will have a remaining lone pair because we know nitrogen has 5 valence electrons in total. I think you should be starting to see the logic here. Oxygen typically is going to make 2 bonds and have 2 remaining lone pairs because these 2 single electrons are available to be shared with the atoms of another element. So here is the moral of the story. Carbon likes to make 4 bonds. Nitrogen likes to make 3 bonds with 1 remaining lone pair. And oxygen likes to make 2 bonds with 2 remaining lone pairs. And we're about to make some examples, or look at some examples, develop some examples. Now I'm going to put the things that I just told you, i.e., for example, carbon likes to make 4 bonds, into practice. We're going to talk about this at the end, so hold that thought over here on the right. Let's look at 2 of these Lewis structures. I'm going to do 2 of them. The other 2 you can work on your own. CH4 is very simple to deal with. It is methane, and we do our skeletal structure. We count up our electrons. 4 plus 4 equals 8 electrons. And we start making our bonding pairs, noticing that we immediately use up all the electrons that we need to use up. We do, in fact, have an octet around carbon. We're done. That was super easy, right? Things get a little more challenging with CO2. So let's, once again, follow the rules. We're going to do a skeletal structure for CO2. We're going to put carbon in the middle. Oops, I shouldn't have drawn a bond yet. Let me take that back. Carbon in the middle. And we're going to count up our valence electrons. 4 for carbon, 6 for each oxygen, 12 and 4 is 16 electrons. And I'm going to bond the carbons to the oxygens. But clearly I have a pretty long way to go here because I've only used up 4 electrons. I have 12 more to go. So let's start distributing these around our oxygen, our oxygens. Okay, have I used up all 16 now? 2, 4, 6, 8, 10, 12, 14, 16. So you might be tempted to stop here. You might say, look at that, isn't that beautiful? I'm done. But we actually have a big problem here, and our big problem is carbon. Carbon has certainly not formed 4 bonds, right? Not only that, because it has not formed 4 bonds and it has no lone pairs around it, which it doesn't really like to have anyway, we do not have an octet. So what we're going to have to do is we're going to have to take lone pairs and we're going to have to transfer them into bonding pairs. So we're going to move them in here and we're going to make them bonding pairs. And that's legal. No one is going to arrest you for taking a lone pair and turning it into a bonding pair in case you were worried about being arrested. You will only be arrested for drawing bad Lewis structures. By me. Okay, now I won't really arrest you, I promise. Okay, so now look at what we have. Let me draw a little line here so we can differentiate between these two things. Once I move these lone pairs, now carbon does in fact have 4 bonds, a desired condition. And oxygen, furthermore, what did we say about oxygen? We said oxygen likes to have 2 bonds and 2 lone pairs. So look at the beauty of that. Not only is this honoring the number of valence electrons that we need, it is also honoring the octet rule everywhere. Carbon has 4 bonds, oxygen has 2 bonds, oxygen has 2 lone pairs. This is a valid Lewis structure. Yay. Okay, so CCl4 is pretty easy. You can do that one on your own. C2H2 is a bit more of a challenge. I'll give you the skeletal structure. C is in the middle. Hydrogens are on the outside. I'm always tempted to draw bonds when I write a skeletal structure, and I really shouldn't. CHH. So do the usual for this, count up the valence electrons, etc. Okay. Now let's move on to nitrogen. What did I say about nitrogen? Likes to make 3 bonds, likes to have a lone pair. NH3, we already did that, so why revisit that territory? Done. Well, I hurt its feelings by crossing it out. Let me undo that. Let's try NF3. NF3. How's that going to look? Doing it again. I'm drawing bonds immediately. That's what happens when you have too much practice drawing Lewis structures. You start cheating madly. Okay. 5 electrons for nitrogen, 7 for each of these fluorines. 5 plus 21 equals 26 electrons. Okay, so now we know how many we need to use. We're going to put in our bonding electrons. We've only used 6 bonding electrons. Okay, so let's start distributing lone pairs. Each fluorine is going to get 3 lone pairs. Have we used up yet all our valence all 26? Let's do a little inventory. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. No! All right, we're going to have to put a lone pair over our nitrogen, which makes a lot of sense, right? Because remember how its individual electron dot thing looks? Okay, so now let's contemplate whether we have, well, now we know we have 26 electrons, so this part is good. Let's contemplate if we have honored the octet rule everywhere. Yes, we have. Nitrogen has an octet. All these fluorines have an octet as well. So once again, we have reached the promised land for a valid Lewis structure, and we can move on and try another one. Let's go for N2. Let's do N2. This one's kind of interesting. I remember it giving me a hard time when I first tried to do it. Okay, so NN, how many valence electrons? 5 plus 5 equals 10 electrons. Okay, we're going to put one measly little bond between these two nitrogens. And, we know that nitrogen likes to make 3 bonds and have 1 lone pair. Something to contemplate. But before we get carried away with that, let's start distributing some valence electrons. To get to 10. So do we have 10 valence electrons here? 2, 4, 6, 8, 10. Yes, we do. Do we have an octet around nitrogen? No, we don't. Not around either nitrogen. So guess what again? Guess what? It's electron transformation time again. I like to call it transformation because we're taking a lone pair and we're turning it into a bonding pair. So now what would this give us? It's going to give us a couple things. It's going to give us 3 bonds, a happy state for nitrogen, and 1 lone pair on either side. Again, look at the beauty of that. We have an octet around both nitrogens. We have a number of valence electrons that matches the number that we needed to distribute. And what else do we have? I don't know, a general state of happiness. Okay, let's turn our attention to oxygen, O2. No, not O2. Let's start with our favorite molecule, water. Another Lewis structure that typically doesn't give us students a lot of trouble, but it does illustrate my point about what oxygen likes to do. H2O. Okay, O in the middle, H is on the outside. How many valence electrons? 8 valence electrons. Make a bonding pair. Put some lone pairs around water. 2, 4, 6, 8. This looks quite nice because we have an octet around oxygen. We've used the appropriate number of valence electrons. What was my point? Oxygen likes to make 2 bonds and have 2 remaining lone pairs. Also honored here. Yay. Okay, now once again, let's try something a little trickier. Let's try O2. I'm going to draw a skeletal structure. What is our number of electrons? 6 plus 6, 12 electrons. Let's draw a bond here. Start putting some electrons around our oxygen. How many have we used so far? 2, 4, 6, 8, 10. Let's do one more here. Okay, so now 2, 4, 6, 8, 10, 12. So that's good. But notice we don't have an octet situation here. 2, 4, 6, 8. For our leftmost, for this oxygen on the left, we don't have an octet. That's not good. We also don't have 2 bonds between the oxygens and 2 lone pairs for each oxygen. So I'm going to take the oxygen that has the more lone pairs and I'm going to move it in here. So that's going to give us wasn't a beautiful dot. Okay. So now we have 2, 4, 6, 8, 10, 12. Octet there. Octet there. Good Lewis structure. Oxygen making 2 bonds, demonstrating that it has 2 lone pairs. But what happens when you might have formal charge? Well, the first thing to do, don't panic. Under no circumstances should you panic. Let's first consider what formal charge is.